Hi, everybody. John Carty, product engineer at Cadence. And this video, I'm going to show you how to use the coupling analysis workflow inside of OrCAD X and also available inside of Allegro X. To get access to this workflow, like all the other workflows, you can go to View Panels and turn on Analysis Workflows. And that's going to give you this panel right here, where you can pick which type of analysis you want to run on your design. And we're going to be talking about coupling right now. Coupling, you can kind of think of as crosstalk, but with less setup and less simulation time. With a crosstalk analysis, you need to assign IBIS models to your drivers and receivers, set up rise time, falls times. It's definitely a more accurate analysis for crosstalk, but you have to spend a lot of time setting it up. Coupling, on the other hand, you don't need to set up any models at all. All you need to do is determine which nets you want to analyze, and you can set that up by doing nets. And you can choose selected nets, so you can pick any nets in your design. You can look at it in terms of flat or hierarchical. Hierarchical is kind of nice because it then organizes all the nets in your design based upon buses. So if you're just analyzing a high-speed interface, you can pick a whole bus at a time. Or you can also choose to do directed groups. And a directed group is kind of a from to's type of statement. So you could say you want to analyze every net from this BGA to these two DDR4 components, for example. So you can select those particular devices, and then it'll automatically analyze every net between them. One advantage of a directed group is it gives you an additional set of analysis output options that I'll show you when I go through the analysis results. Once the simulation is done, you can just run the simulation by hitting Start Analysis. Once the simulation is done, you get the results presented to you in a couple of ways. Like all the other analysis workflows, you get a color-coded overlay on the design canvas. And in this case, it's showing you the coupling coefficient. So what the coupling coefficient is telling you is how much those two traces or more than two traces are coupled together. It doesn't necessarily mean you're going to have crosstalk, because if they're not active at the same time, or if one's not a victim and one's not an aggressor, you won't have crosstalk. But if these nets are going to be active at the same time, then it's pretty well telling you that you're probably going to have a crosstalk problem because these nets are highly coupled together. So for example, you can use this scale here to dim everything else in the design except for these small segments here. And you can kind of see that there's a lot of nets that are going parallel at the same time on the same layer, and also on Z-axis above and below each other. So if those things were active at the same time, you're going to induce a lot of crosstalk from this amount of coupling. And that's what I meant by it's not an actual crosstalk simulation, but it's kind of telling you the same thing, and the setup is a lot easier and it runs a lot faster than a crosstalk analysis. So most users will first run a coupling analysis, clean up their design based upon what they see here, then run a crosstalk analysis and fix anything that the coupling didn't catch. So you can look at the coupling analysis overlays, and you can also look at this in terms of worst case and just victim net. So here you can see, which nets are going to be victim, or which ones have the most amount of coupling from them from every other net combined. Okay, now I'm going to show you the coupling plots that you get. So in addition to the color-coded overlay, you can look at coupling plots and coupling tables. This coupling table is going to show you that, for every net that you have in the design, you can see the total trace length, and you can cycle through every particular net. And then for each net, it'll show you down here the victim trace, the aggressor net, the aggressor trace reference plane, the coupling coefficient, the length, the distance from the start, and the layer in the victim segment. So you can use this as one way to find the worst case nets in your design. You can also look at these coupling plots, which some people find a little easier to understand and digest. This coupling plot is showing you, for every net in the design, it shows you the length of that net, and then at which point in the length it has what degree of coupling. So you can see this particular net here, it's a relatively short net, and it has a very high amount of coupling So you can see this net here, it's a short net and it has a very high amount of coupling for a short distance. Other nets in the design, you can scroll up and down and you can see this particular net is very long, but it doesn't have very high coupling throughout any parts of the net. So using these visions and these plots, you can then work with your design because it's a fully capable layout editor. You could go in here and you could go into the slide mode, for example, and you could grab a trace and just slide it over. So working with these coupling results, since this is a fully capable layout editor, you can go into the design and you can go into any one of the route modes and you could start picking a trace segment and sliding and moving it around to try to improve the situation that you just discovered with coupling vision. You could adjust the layout and then rerun the analysis. Once you run the analysis, you don't have to redo the setup. So you can just run the analysis, find and fix problems, rerun the analysis. That's the real value of these integrated analysis solutions.